Section 6.3, working with normally distributed variables. Distributed variables means the x, the z variable, the x variable. And what we do here, we are interested here in this section to find out the percentage of all the possible observations of a normally distributed curve or norm distributed variable. That lies within a specific range. So what do we do for this, for the x or the x values, x's, let's say, we first try to express it in terms of z. And then we determine the corresponding area. We term the corresponding area under the stand normal curve. So basically we go back probably to the table I showed you in the previous section, which we're gonna also use it in this section. That's called table 2. The book calls it table 2. So here are the procedures to do this. First, we sketch the normal curve. Try to sketch it with the given values. Label the values on the curve. So it's gonna go like this. Maybe they're saying between 1 point something and 1.2 point something, as we did in the previous section. So shaded, label everything. So that sketch, shade the region, mark the x values. So then the x values will be, I don't know if it's gonna be here or somewhere else, but just random example. And then we can express this into the z or convert into z score or z values, label them, shaded, and then from there we can find the z score. Okay, find the z score, and that can be found using the table that I showed. It's shown on the right side, and it's the same one that we showed in the previous section. So let's see how we go over about this. So they will give you x values. So here we're going to determine the percentage of people having an IQ between 115 and 140. 115 and 140. So there's no mention about normal curve or standardized normal curve. So what we have to do is we need to consider these values as x. So x is 115, and then we're gonna standardize this value. So to standardize this value means we need to find its corresponding z value. But they give us information here. They give us the mean and the standard deviation. So from here we can find x z by using the formula x minus mu over the standard deviation. X is 115, the mean is 100, and standard deviation is 16. So if you divide these by each other, that gives us 0.9, I think 375, but you try to round to do this 2 decimal places all the time. So that's 0.94. And we do the same thing for x equals 140. We find the z value, which is 140 minus 100 divided by 16, and that gives us 2.50. So these are the corresponding z values. Now we're gonna go into the shape here and graph them. As you can see, that's 115 and 115, and notice that's the x1. So now you can draw a new curve if you like this for the z. This is z0, and then we have 0.94 and then 2.50. So that's what I'm looking for. Or you might see some people do it this way, the way the book shows here, where they wrote right below 115. 115 was corresponding to 0.94, and 140 corresponds to 250, and that would be the z-axis. So that would be the z-axis. So you can draw another line here and showing the zeros here. 0 should be right below the mean because the mean was 100 for the actual curve. But for the standardized one, it's always 0. So now we need to find the area under that curve from 0.94 if you like to look at it on the right side, and 2.50. So how are we gonna do this? As we did in the previous section as well. So we take to the left of this, because the table gives to the left, minus to the left of this one, and let's see what we get. So to the left of 2.50, what would that be? 2.50. So we're gonna go find the z value, 2.5 and 0, which is this one. So that would be 0.99379. Do not round down or up, just keep it exactly as is, minus the other one, which is to the left of 0.94. 0.94. This is 0.9 and that's the 4. So you go horizontally this way, vertically down, that's the overlapping. 0.82639. And all we have to do is subtract them, and that should give us the exact area I'm looking for, which is 0.1674. So that's what how we use it. So in the previous section, they give us straightforward, they give us the z values, and then we just went to the table, try to find the area, or vice versa. They give us the area under the standardized normal curve, and we had to find the corresponding z values. But here what we have is we are given x values. We're not working in the standardized normal curve, but rather we are working in a different curve. And then what we have to do in order for us to use the or the tables here is we have to first standardize it, convert the x's into z's, and then use the table to find the area, as we did in the previous section. So another thing here we need to learn in this section, how can we visualize the normal distribution? We are going to introduce something that we already learned about it before. We have, if you got a data set that is roughly or distributed roughly bell-shaped, then we have the properties that follow up. That's called the empirical rule for variables. So we have the empirical rules for variable, which says about 68% of the data will fall within one standard deviation. You've seen this before. And then about 95% of the observations will fall within 2 standard deviations. That's what this means, within 2 standard deviations, above the mean and below the mean. And about 99.7% of data or observations will fall within 3 standard deviation. So this is the graph here to show you that. And then we did cover this before, and then we gave the exact numbers, if you remember. Like we drew a line here was 68, each one 34, and then this was 13.5 on each side, and so on and so forth, as long as it fulfills these numbers. So why do we need this here? What is this for? Why is this introduced here? Now, any variable whose distribution is about or roughly bell shape, then the empirical rule can be used. So the empirical rule, this empirical rule can be used as long as can be used for any distribution that, as long as it's a bell shape. So the empirical rule can be used. And I'll show an example in a minute how we use it. But for normally distributed variables, we use table 2. So this is important stuff. Now, what do we need the empirical rule for? We can go back and solve the same example. You know, back to the example, I think the mean was 100, about the IQ example, and the standard deviation was 16. So from here, and then we were interested to know about between 115 and 140. But in general, what's going to happen in general? So if you do if you go one standard deviation above and below the mean, so this is the mean 100. If you add one standard deviation, that would be 116, and below the mean, that's 84. So this tells us about 68% of the observations will fall in here, because as long as the shape is almost or roughly bell shape. So then 68% of the people will have, so 68% of the people will have IQ or IQs between 84 and 116. So that's how the empirical rule helps. If you know the mean and standard deviation, you can find or you can estimate the percentage of the people that we can get some percentage about how many people or what's the percent of the people who have that their IQ falls between two different numbers. What about two standard deviations? So if I go mu plus one standard deviation, I just found it was 100 plus 16. That's where I got 116 from. But if you do mean minus this, that's 100 minus 16, and that's 84. But if I do two standard deviations, so the mean minus two standard deviations, the mean is 100 minus 2 times 16. Let's see, that's 100 minus 32. So it's basically you're subtracting twice, so that would give us 68. If you do add it twice, two standard deviations, that's 100 plus 2 times 16. So that would be 100 plus 32, so that would be 132. So if you graph it, if we graph it like this, the mean in the middle, like so, and then we have 132 and 68. So in between these two, what we have, about 95% of the people will have an IQ between 68 and 132. And we can do it for 3 standard deviations. Overall, all of them would be like this: 100, add 16, add another 16, 132, add another 16, 148, subtract 16, 84, subtract 16, 68, and then if we subtract 16 again, that's 52. So that's our bell shape, and then one standard deviation. 68% of the people will have an IQ between 84 and 116. About 95% of the people will have an IQ between 168 and 132. 99.7 of the people will have an IQ between 52 and 148. That's what the empirical rule is for. Another thing we need to learn in this section is basically how to find the observations for a specific percentage. Like they give you the percentage and we need to find the specific information. So basically we need to find the X value. If we go back to the formula, X minus mu over the standard deviation, and cross multiply like this. So X minus mu equals Z times the standard deviation. And add mu to both sides. Mu plus Z times standard deviation. So if we know the Z value, the standard deviation, and the mean, we can find the X value. We can find the X value for this. So this is kind of backwards. Before they give us X here, and we found Z. Here they give us Z, and you need to find X. For example, let's say obtain the 90th percentile for the IQs that we were working on earlier. So what is percentile? Sometimes you go take a test, maybe GRE or GMAT or CCAT, like those tests for college admissions. And they tell you you have to score in the, or your score falls in the, you scored in the 90 percentile. This means you did, on the day you took the test, so many people took the test on the same day, you did better than 90% of the students who took the test on that day. That's what 90 percentile means. You did better than 90% of the students who took the test on that day. That's percentile. So what is this percentile? Of course, the mean still the same as before. This will be given, and the standard deviation is 16. And what this is really the percentile on the graph is, if we draw the bell shape, and this is the mean, 100. And the 90 percentile, that's think about it as 90%. 90%, that's gonna be the area. So the area is 90%. Okay, so that's 0.90. So 0.90, remember the area under the whole curve is 1. So this one maybe is the 0.90 to the left, like so. And remember, what are we looking for? What we're looking for is the x value. We're looking for the x value. So now we still in the x range, and for the z-axis, the z-axis, this is 0. So we first to find the x value. If you look at the box formula, you need the 3 things: mean, standard deviation, and z. We do have the mean, we do have the standard deviation. We still need to find the z. So what we're gonna do is we need to find the z that corresponds to that number. Okay, this is called the p of 0.90, kind of like the 0.90 is the area to the left of that one. So what we have to do now, we need to find the z-score. What is the z-score or the z using the table to find that? So we need to go to the table back to the table up there, table 2, and find the z-score or the z value. So we need the z value is the area is 0.90. So I see 0.899 and 0.90. So what you can do, if you like, you can subtract them. So do here on the side, I'm gonna do 0.90 minus the first number, 9973, and let's see what that gives us. So let's calculate that out. 0.90 minus 0.87993. So that gives us 0.00027. And then the same number, subtract 0.9147. And let's see what that gives us. Of course, it's going to give you negative. You can do it the other way around if you like. 0.90, that's 0.00147. Notice this number is smaller than this. So this means, this tells you that this number is closer to 0.90, is closer. So then what we do, if we go this way horizontally and up vertically, that gives me 1.28, 1.28. That's the z value, 1.28. So scrolling down, we were able, using table 2, is 1.28. Then the x is the mean plus z times the standard deviation. So x would be, the mean was 100, so 100 plus z is 1.28 times the standard deviation, which is 16. And that would give us 100 plus. If we multiply these together, that gives us 20.48, and adding them up, that would be 120.48. That's what it is. So this means the 90th percentile for the IQs is about 120.48. So this means 90% of the people have an IQ below 120.48. That's what it means. So about 90% of people have IQ below 120.48. This is a good stuff, important stuff, and it has applications as well for later sections.